Welcome to AI Training and Learning Basics. As a reminder, the focus of this material is simple concepts that everyone can relate to and learn from, not 100% precision. The goal is to make AI an approachable topic that a broad range of people can achieve comfort with. With comfort comes acceptance and adoption. When it comes to machine learning, the big picture concepts to be remembered are training and inference. In the training phase, a model receives training data which it responds to with output. An algorithm then examines the output, and if the output is not what is expected, the algorithm changes the internal settings of the model. When the output data is close enough to the input data, then the training phase is complete. It is important to remember that the output is not necessarily in the same format as the input. For example, the input data might be an image of a cat, and the output might be a code that indicates cat, not an image of a cat.
When the training is complete, the model can then be used for real-world applications, creating output in response to new data it has not seen before. This is referred to as inference. Before a model is used for inference, various optimizations may be made to make the model smaller or faster, but these optimizations do not impact the overall use or goals of the model.
To recap, during the training phase, an algorithm adjusts the internal settings of a model until the model is producing expected outputs. During the inference phase, the already trained model is used in real-world applications. It is helpful to think of the algorithm as only being in the training phase. Some implementations break from this approach, but it is a good general approach to thinking about the difference between training and inference. Before AI can do anything for us, it has to be trained to do something. Think about it like a student going to school to learn.
In AI, we refer to the student as the model, the trained intelligence we will use to answer questions, solve problems, and make predictions. Who is training the student? The teacher, which in AI we refer to as an algorithm. The algorithm adjusts settings in the model based on the results from testing the model. In classification problems, for example, what is in this picture, the data is examples of the objects we want AI to learn to recognize. There are other types of data and learning in AI, but we will start here because it is a kind of AI that is commonly spoken about. Also, the teacher and student analogy works well in classification problems.
The student, or the model, is an artificial neural network. In nature and human-designed innovations, incredible capabilities arise from connecting simple elements. It is the same with artificial neural networks, which are based on how scientists believe the human brain may work. Imagine a teacher showing a student a picture of a cat and the student's brain creating pathways that will recognize a cat the next time it sees one. Conceptually, this is how AI neural networks also work.
In a human brain, some pathways are preferred over others for a given task. This happens through a biological process that strengthens connections in response to learning. In artificial neural networks, the process is not biological, it is digital. So the preference of a connection between two neurons is indicated by a number, referred to as a weight. The weights, or the strength of connections between neurons, are set by the algorithm iteratively as more data is processed. The algorithm makes changes based on errors it observes in the model, in this initial example, correctly identifying an object in an image. It can be helpful to think of an algorithm as a computer program that is using a mathematical function to determine how the weights should be set.
A neural network is a complex structure that arises from connecting simple pieces together. Each circle in this diagram is called a neuron or a node. In this diagram, there are 4 layers. In practice, there can be many more based on the design of the neural network. There is the input layer where some digital information, for example an image of a cat, are transformed into descriptions the different parts of the input. For example, an image of a cat might be transformed into information about the color and intensity of each bit in the image, and there might be an input node for each bit. The output layer is, in the case of a classification problem, a node for each prediction about the probability of what that image is.
The hidden layers are all the layers between the input and output layer. In some models, what is going on in the hidden layers is somewhat understandable. In other models, it is hard to impossible to know what is going on. Now we will add to our previous discussion of weights with a related concept, activation.
Each node in the hidden layers is receiving information from multiple nodes in the previous layers. Like the previous layers, though, the node must output one weight and one information flow. We call the output of a node the activation level, and it is derived through mathematics equations that evaluate all the inputs and creates one output.
Some people like to use the analogy of a water pipe and a tap that controls a valve, and hence the flow of water out of the tap.
We now look at a convolutional neural network so we can dig deeper into concepts. A CNN is a common model type for image recognition, where mathematical calculations may be applied to regions of an image to detect such things as sharp transition in intensity. The first stage of the process is extracting features from an input, for example, a picture of a cat. In this case, the features would be properties of pixels such as color, intensity, etc. In the case of LLMs, the features are different, as we will explore in other modules. Next, those features are sent to the input layer of a neural network. It is convenient to think of there being one input neuron for every feature. In deep learning, there are multiple layers, with successive layers recognizing increasing complex concepts. For example, while the input layer may deal with individual pixels, successive layers may deal with a region of the image or constructs such as edges and lines. As information flows through successive layers, the features of an animal emerge, for example, ears or a tail, perhaps even fluffy fur, until finally, the model predicts with a high probability that the image is of a cat, and the other animals the model knows about have a lower probability. It is convenient to think about each output layer neuron as being an animal the model knows about, with its unique probability. In really large spaces, the number of output neurons may be constrained, which we will discuss later. In this example, we were demonstrating one use of neural networks, image recognition, where the desired output is recognition of a known image type, a cat. In other uses, the output might be the next word, the temperature, or a stock price. In some cases, post-processing is required for further refinement. The training is done, the teacher moves out of the picture, and it is time to see what the student can do. The student, or the model, is sent an image of a cat. The image is broken down into numerical representations of color and intensity. This information flows through the pathways in the model until an output is created.
The model will usually be trained on multiple objects, so it creates output that indicates the probability of the input image being one of the objects it was trained on. In this example, the output would indicate there is a high probability the image is a cat, and a low probability the image is something else, for example, a flower. The AI product that is sent the output may use the highest probability, or it may use different probabilities to create some randomness or uniqueness in what it is doing. Those kinds of choices are up to the AI product. However, in this case, if the desired result was knowing the object in the image, then the highest probability would likely be used.
To recap this section, think of the algorithm as a teacher telling a student what something is. More technically, think of the algorithm as a computer program using a mathematical function to iteratively design the internals of a model so it can do something, in this case, recognize an object.
Think of the model as a student, something that has been trained for a specific purpose. The model is the trained neural network that can perform the required task, for example, recognize an object. Weights are the strength of a connection to another neuron, and in classification tasks, the output is a collection of probabilities, the probability that an object is this or that.
I hope you have enjoyed AI training and learning basics. If you would like to see a short video on another AI-related subject, then make a suggestion in the comment section where this video is posted. Goodbye and thank you.